has many beautiful and extremely important results, of which I would like to mention his work with tau, in which they prove that there are arithmetic progressions of arbitrary length among the primes. Now, today, he will talk about approximate algebraic structure.
Thank you very much, Lazzi. Am I audible? Yes? Okay, so let me just begin by saying that it is, of course, a huge honor for me to speak here. And the main reason that I get to speak here is that I have amazing taste in co-authors. So I'd like to thank my co-authors, 4 of whom are speaking at this Congress. So thank you very much. So what I'd like to talk about today is approximate algebraic structure. This is part of the subject that we call additive combinatorics. And the main questions we ask are the following questions. So what do we even mean by this notion of approximate structure? What's an approximate group, field, or polynomial? What can we say about them? And then when we finish with that, well, what use is it? So I hope to touch upon those 3 points today. Here's a plan of my talk. I'm going to mainly talk about what we call approximate groups. So I'll start by introducing those and giving a few examples. And then I want to give a very personal selection of 3 different applications from quite different areas of mathematics of these. So I'd like to talk about some questions about points and lines, geometric questions. Talk a bit about random walks in groups. And then I will turn my attention to prime numbers, patterns in prime numbers. And then I'll talk a little bit about a different type of approximate structure, approximate polynomials. And then finally, seeing as it's the ICM, I want to announce a new result at the end of the talk. So let's talk a little bit about approximate groups. So here's the definition that hopefully most people are familiar with. Not a definition. This is a statement about when a set A in a group is a subgroup. So I think this is something that's familiar to everybody. If it's non-empty, and if it's closed under multiplication and inverses, that's what it means for a set to be a subgroup. So an approximate group is a variant of this concept in which you don't ask that A1, A2 inverse always lies in A, but just that that happens most of the time. So we'll say that A is an approximate group if for most pairs A1, A2 in the set A, A1 times A2 inverse also lies in A. Now, that's not a rigorous mathematical definition, of course. What does most mean? So to quantify it, I need a parameter delta. So I'll say that A is a delta approximate group if the proportion of pairs for which this closure operation holds is at least delta. So the parameter delta will be different in different applications, and I'm not going to dwell on that too much. Sometimes it might be nearly 1. It can't be bigger than 1. Other times it might be 0.01, and then some other times it may even be a little bit smaller than that, quite a bit smaller than that. Just so we don't get confused, I'm going to sometimes be talking about just general groups, but often I'll be talking about abelian groups. And when you have an abelian group, you write the group operation with a plus and the inverse with a minus. So just to be clear, if you're in an abelian group, an approximate group is one for which, for many pairs A1 and A2, the difference of A1 minus A2 also lies in the set A. So this is the key notion I'm going to be talking about. How about then some examples? The most basic example of an approximate group is just a group itself. So any group is a one approximate group. It's completely closed under products and inverses. That's a little bit trivial, of course. So the first non-trivial example would be if you take a progression in the group. So if you're in an abelian group, you can look at all of the multiples of some fixed element G, and provided that set of elements is all distinct, then you get a 3/4 approximate group. And here's a picture of one in the integers. So this is just an interval of integers. And I calculated, I hope correctly, that the proportion of pairs A1 and A2 in this set, for which the difference also lies in the set, is 37/49, which I hope is bigger than 3/4. Okay. The next example is a higher dimensional variant of that. So what I've written here is a 2-dimensional progression, but you can also make these in d dimensions. So suppose again that you're in an abelian group, and consider a set A that's generated by 2 elements, G1 and G2. So again, if those elements are all distinct, then what you have is a 1/2 approximate group. And here's a picture of one of those. So it looks like a progression of intervals or a progression of progressions. And in this particular example here, well, just to relate it to the definition, here I took G1 to be 1, G2 to be 9. And I computed that the proportion of pairs A1 and A2 in this set, for which the difference also lies in this set, is this weird fraction which is also bigger than 1/2. So this is also somewhat closed under multiplication and inverses. And as I remarked, you can generalize this to higher dimensions, to d dimensions. Things get a bit more exotic than that. You can make examples in non-abelian groups. And the background here is a picture that I stole from something called the Simons Institute for Algorithms or something. It's a depiction of the Heisenberg group. And inside the Heisenberg group lives something called a nil progression, which is also an approximate group. So the Heisenberg group is what I've written here. This is 3x3 matrices over the integers. And let's pick 3 elements, 3 very natural sort of basis elements for this group. And this set A that I've written down here is kind of a non-abelian variant of a 3-dimensional progression, if you like. So G1, G2, and G3 don't commute, but they almost commute. And if you choose the sizes of those progressions in a suitable fashion, then this will also turn out to be an approximate group. There are many variations on this, but there's a particular choice of parameters for which it works. And you can generalize this to other nilpotent groups. The Heisenberg group is a very simple example of a nilpotent group. So I've given various examples of these approximate groups, genuine groups, and these progressions. And they're all somewhat rigid objects, a little bit algebraic at least. But unfortunately, that's not true in general. So this notion of an approximate group is not very robust. It's a very rough notion. So one thing you can do is take an arbitrary approximate group and just throw in some completely random elements to it. So they could be anywhere. So take a progression of integers and then throw in 10 to the 10 and 100 to the 100. So that will still be an approximate group. And also, you can delete a few elements of the set A. So that, in fact, typically, if you take an approximate group and throw away half its elements, you still have an approximate group. So the next picture is supposed to encapsulate for you everything I've said so far. So here's somehow what you should think of as a typical approximate group. It's a 2-dimensional progression. That's the grid, the black lines, to which I've thrown in a few extra points. Those are the ones over on the right. And then I've deleted a few points from the grid as well. So anything like this, and some non-abelian variants of this as well, will be an approximate group. So because of this roughness I've just mentioned, you can't hope to really classify approximate groups. The best you can hope for is a kind of a rough classification that would have to include things like this object here. But it turns out there is actually such a thing. And the theorem's a bit complicated to state, but it basically says that I've already shown you all of the approximate groups in some sense. So all approximate groups are genuine groups, progressions, nil progressions, and then things you get by adding a few elements or deleting a few elements. And if you're thinking about delta approximate groups, this is the quantitative notion, then the number of different types is bounded in terms of delta. So I'll come back to that theorem in a moment. That's a very deep theorem. A much simpler theorem is that actually, if you have something that's basically a one approximate group, so with you're really very, very close to closed under multiplication, then you're very close to a genuine group. And that's a theorem that I'll be applying a bit later on due to Freiman and Fournier. So this rough classification theorem is the work of very many people, and it involves ideas from many different areas, and I'm not going to be able to talk in any detail about it. But I want to really highlight here the names of Freiman and Ruger, who essentially worked out the abelian case of this. So they classified all abelian approximate groups. And they did this a long time before any of this was fashionable. It's very remarkable work of Freiman and Ruger. And then all of these other authors were essentially generalizing this to non-abelian groups. It's an area where much is left to be done, and particularly with regard to the quantitative issues about which we know very, very little. So that's really all I want to say about approximate groups in general. You don't need to remember any of that, but it would be good if you remember that an approximate group is basically something that's almost closed under the group operation. So it's a subset of a group, almost closed under products and inverses. So now I'll talk about something totally different. This is my first application of approximate groups. So this is something I dug out of the basement of Cambridge University Library with some effort. This is the Educational Times 1893, question 11,851. And well, I'll leave you to read this. This is J.J. Sylvester is asking the following question. If you have finitely many points in the plane, they could all be on a line, but if they're not all on a line, must it be the case that there's some other line that passes through precisely two of those points? So that's what Sylvester asked. So to illustrate that, here's a collection of 9 points in the plane. Sorry, 7. It's embarrassing. They're the black dots. And hopefully the green dotted lines are lines that pass through more than 2 points of the set. But you can see that there are nonetheless 3 red lines that pass through precisely 2 points of the set. And Sylvester's question is this always the picture? So must you always have red lines? And it's a very famous theorem, usually known as the Sylvester-Gallai theorem, that indeed that's the case. So if you have a finite set of points in the plane, and if they're not all on one line, then there is indeed a red line through precisely 2 of the points. But a question that's very natural is, how many such lines must there be? So in the example I showed you, there were 3, 7 points and 3 lines. What's the truth for n points? And there was a conjecture of Dirac and Motzkin, which stated that the answer is always at least n over 2. Now, if you're paying any attention, you'll say that obviously that's false. I just showed you 7 points with 3 lines through 2. But this is supposed to be the case for n sufficiently large. And this is now a theorem by Tau and myself. Indeed, if you have n points in the plane, and if n is big enough, then either they're all on a line, or there are at least n over 2 red lines between pairs of points. It's not at all obvious that n over 2 is the right answer in this problem, but it turns out that it is. And the examples showing that this is sharp look like this. This is called Boruchki's example. So this is an example of an ellipse and a line, and there are 6 points on both of those, so 12 points in total. And there are only 6 red lines, 6 lines through precisely 2 points. Now actually, it's conjectured that n0 can be 14. So I showed you a configuration with 7 points and 3 red lines. There's another configuration with 13 points and I can't remember how many lines, maybe 6. So it's possible that n0 is 14, but we fall just short of proving that in our paper. Now, what I want to draw attention to here is the fact that this Boruchki example, made up as it is of an ellipse and a line, is those points are on a cubic curve. It's a reducible cubic curve, so it doesn't look like one of the elliptic curves that Mandel-Bhargava showed us, but it is a cubic curve. And actually, you can look at elliptic curves like the ones that Mandel-Bhargava showed us. Here is such a curve. And they don't do quite as well as this Boruchki example, but they nonetheless have quite a small number of red lines. So here's an example with 8 points and only 7 red lines. So the red lines being the ones through precisely 2 points. So cubic curves have something to do with this problem. And, well, I'm going to sketch only incredibly roughly how Tau and I proved this theorem. The first step is to show that actually if you have any set with not very many red lines, so let most say 100 times n red lines, lines through 2 points, must basically lie on a cubic curve. So 100n is small. In general, if you put down n points at random, you'll get nearly n squared, n choose 2 lines through just 2 points. So in a sense, that's the most interesting part of the proof, actually, but I'm talking about approximate groups, so I'm not going to touch upon that. Let me just say that it relies on a close analysis of a proof of this theorem of Sylvester-Gallai due to Melchior, which uses Euler's formula and some very classical algebraic geometry. But the approximate groups come in when you come to analyze these cubic cases. So if you have n points on a cubic curve, how many ordinary lines, red lines, must there be? And this is where the theory of approximate groups comes in. So to see why that is, let's look at an example. So a very simple example of a cubic curve is y equals x cubed. Let me take a set of n points on there, which will look like this, parameterized. And can it have not very many ordinary lines? So when is a line not an ordinary line? Well, when it passes through 3 points on the curve. And these cubic curves, very much like in Mandel-Bhargava's talk, have a kind of a group law on them. Actually, this cubic curve is singular, but it still has some sort of a group law on the non-singular points. So the relation between 3 points for them to be collinear is that the sum of their x coordinates is 0. So if your set A has few ordinary lines, then this is telling you precisely that for most pairs A1 and A2 in A, minus A1 minus A2 also lies in A. So that's very, very close to A being an approximate group. There's an extra minus sign, but let me just pretend it's not there. So let me say A just is a delta approximate subgroup of the real line with delta roughly 1. But we had a theorem of Freiman and Fournier which told us that all such approximate subgroups with delta very close to 1 they must be close to genuine finite subgroups of the real line. And there just aren't any interesting finite subgroups of the real line. The only one is 0. And so that means that A has to be extremely small. So in this way, you've essentially classified subsets of a cubic curve with few ordinary lines. Let me do one more. Parabola and a line. So a parabola and a line is also a cubic curve, given by this equation. Let me take a set P on there. So this is a parabola and a vertical line. So take a set P that lies on the union of a parabola and a line. Can that have few ordinary lines? Well, again, the collinearity relation here is given by something like a group law. If those 3 points that I drew there are collinear, then B is minus A1 times A2. So if this set P had few ordinary lines, then for almost all pairs A1 and A2, you'd have that minus A1, A2 lies in B. And now this means that A is an approximate subgroup of multiplicative R, roughly. And again, by Freiman-Fournier, it must be close to a genuine subgroup of multiplicative R. And there are, again, not very many interesting ones. So you don't get good examples of sets with few lines through 2 points from either cubic curves y equals x cubed or from a line and a parabola. And the other cases, there is a similar analysis, and using a more detailed classification of approximate groups, you eventually prove this Dirac and Motzkin conjecture. That's all I want to say about that. Let me turn now to something totally different. Random walks on groups. So the aim here is take a finite group, G, and suppose it's generated by some set S. So everything in G is a product of elements from S and their inverses. But what we want to know is how quickly S generates the group G. So how quickly and how uniformly does that set S generate G? Well, how do I measure that? What I'm going to do is look at a random walk on the group G with generating set S. And actually, because it makes nicer pictures, I'm going to look at the lazy random walk. So what this walk does is it starts at the identity, E, and then it moves. So in the picture I'm going to draw, S is going to consist of 2 elements, A and B. It stays where it is with probability 1/2. And then it might move to A, or to B, or to A inverse, or to B inverse, all with equal probability. There. I don't know how well this comes out, but there are supposed to be different shades of red for how likely you are to be at a point. So that's the first step of this lazy random walk. And then the second step looks like this, and then you continue, and so on. So x2 is the random variable on this set of points, and the probability of being at a given point is essentially how red that point is. Now, the picture may not look like this always, because sometimes these walks come back on themselves. And in fact, if the group G were abelian, then already some of the pairs of points here would coincide. So the walk, in that case, spreads out slower. So I want to know when it spreads out quickly and fills up the whole group quickly. So to measure that, I introduce something called the mixing time. So the mixing time is basically how long it takes for this random walk to get close to equidistributed on the group G. So the smallest m, for which xm, which is the random variable of the walk after time m, is close to the uniform distribution. It doesn't really matter how you define close. I mean, it makes a small amount of difference, but there are many different ways of doing it. It's not very important. So how small could the mixing time possibly be? Well, the random walk, let me go back. So suppose the group could be enormous. It could be the size of this room. And after 2 steps, I can't have filled up this room with these little red balls. I've actually only filled out 12 points, maybe 16 points. And you can compute that actually after j steps, the number of points I've hit is 2 times 3 to the j. And so you can't even fill out the whole group until exponential time. Until logarithmic time in the size of the group. So at the very least, just to fill out the group, you have to have gone log times the size of g steps along this walk. And it turns out, remarkably, that for simple groups, non-abelian simple groups, that's actually sharp. So there's an extraordinary theorem by Kasabov, Lubotsky, and Nikolov, which states that in just any finite simple group, if it's not abelian, there's a set S of constant size, a constant size set of generators which, independent of the group, which mixes essentially as quickly as it possibly could. So just a constant times log g. That's a very deep theorem. Amongst other things, it depends on the classification of finite simple groups, and a lot more on top of that. So there's that theorem stated again. Now the star here is, there was actually one small family of finite simple groups which the theorem of Kasabov, Lubotsky, and Nikolov did not cover. And that's a family called the Suzuki groups. And it turns out that the theory of approximate groups could be used to clean up that case. So that's to remove the star and handle all finite simple groups at once. And that's a theorem of Emmanuel Boyard and Terry Tao and myself. And we use something called the Bourgain-Gambard method. And I'm going to tell you a bit about the Bourgain-Gambard the original method of Bourgain and Gambard. And we needed their method as well as some study of approximate subgroups of 4x4 matrices in characteristic 2. That's where these Suzuki groups lie. So Bourgain and Gambard proved other very nice statements about rapid mixing in finite simple groups. So if you take this group PSL2 of FP, that means 2x2 matrices over FP with determinant 1 modded out by plus minus 1. And if you just pick 2 random elements in that group, then those essentially, the random walk on those 2 elements will generate the group as quickly as it possibly can, up to a constant. And the theory of approximate groups has allowed the proof of further theorems. So I want to just mention a result of the authors I mentioned before, and Bob Guralnick, who's here, which generalized this to bigger matrices, higher rank groups. So I'd like to talk about this method of Bourgain and Gambard for proving rapid mixing of random walks on groups, which is a very nice application of approximate groups. So take your group G, and Bourgain and Gambard were taking 2x2 matrices, and then start a random walk on the pair of elements A and B. And I'm going to write B sub t for the set of points that I've visited at time t. So the big circle is supposed to represent the group G, and I've drawn B naught. So B0 is where the set of points visited after time 0, and that's just the identity. And that's the set of points visited after time 1. That's the set of points visited after time 2. And at this point, my ability to use TIKZ picture gave up on me, so I cheated. So that's the set of points that you visited after time 2. And then after time 4, we've gone a bit further out in the group. After time 8, we've gone even further. That's supposed to be a light blue. It doesn't look very light blue to me. But it may be that this is what happens. So you just keep expanding out in the group, and pretty quickly you fill up the whole group. And that picture is supposed to represent that happening. So that's rapid mixing of the random walk. That's good. So what if that's not the picture? So here's another possible picture. Let me remind you that B sub t is the set of points the walk has visited after time t. You start at the identity again, and after time 1, after time 2, time 4, time 8, and then something weird happens and you get stuck. So somehow, suddenly you stop expanding out, and you can see it's going to take a long time to fill out the whole of the group G. Now, what does it mean that I got stuck there? Well, the set of, so B8 is the set of words of length 8 in the generators of the group, and B16 is the set of words of length 16. So B16 is the product of 2 copies of B8. So if you got stuck in this picture, that means that whenever you take the product of 2 elements in B8, you basically get back in B8 again, or at least that's quite likely. And that's just precisely saying that B8 is an approximate group. So either things are good, the random walk filled out the whole group quickly, or you get stuck at an approximate group. And we need to rule out that second possibility. So to do that, we need to understand what the approximate subgroups of these groups of 2 by 2 matrices are. And there's a theorem about this, independently proven by Poyard, Tau, and myself, and by Pieber and Szabo, but very strongly based on foundational work by Harold Helfgott. Roughly speaking, it says that if you have an approximate subgroup of a group of matrices G, if it doesn't fill up almost all of G, then it's stuck inside a proper subgroup of G. So it takes a little while to parse the statement of this and realize that it's non-trivial, but somehow we don't know anything about the approximate subgroups of G, but we've got algebra to tell us about the genuine subgroups of G. So knowing that you're stuck in a genuine subgroup is much, much more information. So could this happen to us? Could our random walk after time t be stuck inside an approximate subgroup of G without having already filled up all of G? And in other words, by the theorem, can our random walk get stuck inside a subgroup? Well, let's see if that can happen. And here's where my picture drawing ability just collapsed entirely. This is supposed to be 2 by 2 matrices over fp squared, but of course it's just a circle, but bear with me. Here is supposed to be the subgroup of upper triangular matrices, which is an example of a subgroup of this group of 2 by 2 matrices. So could you have a random walk that's stuck inside this subgroup? Well, you could, but it would have to be a very thin and constrained random walk. And if you pick the generators of the random walk at random, that's unlikely to happen. Now, that's just one subgroup, the upper triangular matrices. There are other subgroups. And this is where things are even harder to draw. You can have the set of matrices over some subfield. So the original group was matrices over fp squared, but you could have matrices over fp. Could you be stuck in there? Well, again, you could, but that's a very unlikely situation to happen. And again, for almost all choices of the generators of the random walk, that does not happen. But let me just reiterate that it's genuine algebra, so classifying the subgroups of SL2FP, that allows you to draw these conclusions. Once you have a theorem saying that approximate groups are stuck inside genuine groups. That's not the end of the Bourgain-Gambit method. So all I proved there, well, actually I proved nothing whatsoever, but if I elaborated upon what I told you, I would prove that a random walk fills out the group in time log the size of the group. That's not the same as being equidistributed on the group. Filling out is less information than equidistributed. So the mixing time is going to be bigger than the filling time in general. But there are some arguments of Sarnak-Chue and of Gowers that allow you to, once you've almost filled out the group, you then become equidistributed quite soon after that by a representation theoretic argument. And again, the key ingredient is algebraic. You need the fact that these groups, like SL2FP, have no small dimensional irreducible representations. So again, I've really just scratched the surface of this study of random walks on groups because I wanted to show you an application of approximate groups. There are many other directions one could take, and I just want to mention in particular something called the affine sieve, which is an exciting sort of non-abelian topic in analytic number theory. And the main players there, Bourgain, Gambard, and Sarnak, and Vayu, and Salehi-Gossafidi. And now for something completely different. So I'm going to now jump to talking about patterns of primes and approximate polynomials. So I'm going to ask a question that I hope your reaction is, why on earth would you be interested in this question? So, is there an arithmetic progression of 100 primes with prime common difference? Now, Terence Tao and I proved 10 years ago that there is at least a progression of 100 primes, but could you have prime common difference? Well, obviously not. If you have an arithmetic progression of primes, the common difference is going to be even, and also a multiple of 3, and in fact a multiple of 97 as well. So, why have I asked that question? Well, it turns out that whilst you can't do that, you can get close to that. So it follows from a long series of papers that I've written with Tao and with Tammy Ziegler, who's here. You can find 100-term progressions of primes in which the common difference is nearly a prime. It's merely 100 factorial times a prime. So in other words, it's a prime times a few factors like 2, 3, 5 that have to be there. So I'm going to call those doubly prime progressions, and the reason I'm interested in them will become apparent. And there is an asymptotic for those. That's a certain constant times n squared over log n to the 101. So the 101 is because you're basically making 101 things prime. Each of the 100 terms of the progression and the common difference of the progression divided by 100 factorial. Now, I very much doubt that anybody's interested in the constant, but that's what it is. I didn't work it out what it is in decimal. So I want to talk a little bit about the proof of this theorem. So remember that a doubly prime progression is a 100-term progression of prime numbers whose common difference is a prime times 100 factorial. And it turns out that the right way to think about this question is to ask a much more general question, which is probably the interesting question here. I mean, who cares too much about these doubly prime progressions? So I'm going to just look at general averages of functions over linear forms. So in this expression, psi1 up to psi t are linear forms, and the fi's are some functions. And let me just show you how this links to the previous slide. So if you take 101 of those forms, and they're going to be forms in 2 variables, n1 and n2, and the functions, all 101 of the functions, are the characteristic function of the primes. So that's 1 if you're a prime, and 0 if you're not a prime. And then the linear forms, well, the first 100 of them are there to tell me that I've got a progression of length 100. And then the final term, n2, I also want to be a prime. So that's how I make progressions with common difference 100 factorial times a prime. And then k is just, it's a polytope that counts where I want to count these configurations. So I want you to at least believe me that the right thing to study is this much more general question about averages of linear forms. And those averages may be studied using what are called approximate polynomials. So let me talk about approximate polynomials for a bit. and mention very briefly how they're actually intimately connected with approximate groups, which is why I'm talking about them today. So at the top there, I've just written the average again. This is the average I'm interested in studying. So just remember that the fi's are just some bounded functions on the interval 1 to n, and the psi's are linear forms. So it turns out that the right question to ask is not, can I estimate this average, but can I show at least that this average is small in some situations? So why is that the right question to ask? Well, very briefly, for a general situation, you can usually decompose your functions fi into pieces. And some of them will be structured pieces, and then you can evaluate the term explicitly, the terms coming from those pieces. And then there are some other pieces that are random and highly oscillatory. And usually, because there's a lot of oscillation, those terms will be small. So the question is, how can I prove rigorously that those terms are small? So the question is, can I come up with a criterion for showing that this average along linear forms is small? And Tim Gowers came up with such a criterion using the Cauchy-Schwarz inequality and nothing else. Just clever applications of the Cauchy-Schwarz inequality. He showed that if this is not small, then the functions fi must all have some behavior that we call approximately polynomial. And I will tell you what that is on the next slide. So what is an approximate polynomial? Well, a polynomial, let's say x squared plus 3x, if you difference that 3 times, or discrete differentiation of that 3 times, you get 0. And the definition of approximate polynomial is based on that observation. So it's a function, the definition takes a little while to parse. So it's a function for which when you take s plus 1 multiplicative derivatives, and the multiplicative derivative of a function is the thing I've defined at the bottom there, f of n times f of n plus h complex conjugate. Take s plus 1 derivatives of your function and average over all possible choices of the derivatives and the point that you're evaluating at. And if that average does not cancel, so if it's at least delta, then you say that you've got a delta approximate polynomial of degree s. And for people who've, a number of people here may have seen the term Gowers norm. So actually this average of derivatives is what's called a Gowers norm. Now when I talked about approximate groups, I gave a definition and I said, when delta equals 1, this just degenerates to the usual definition of a group. So it's a natural approximatization of the definition of a group. So, and it turns out that actually what I've shown you here is a natural approximatization of the definition of a polynomial. So this is supposed to be an exercise. It's not very hard. One approximate polynomials are just genuine polynomials, or rather phase functions of polynomials, e to the 2 pi I times a polynomial phase. So the language that I've used is at least reasonable. So I've told you what an approximate polynomial is. Now let me do what I did for approximate groups and tell you a little bit about what they look like. And the situation is actually very similar to approximate groups, in that not all approximate polynomials look like genuine polynomials. And already in degree 2, in fact in degree 1, approximate polynomials do look like genuine linear phases. But in degree at least 2, there are these more exotic examples where you're allowed not just polynomial operations, but also bracket operations. And this bracket here I should have written on my slides. The bracket is fractional part. So it's the fractional part function. So I wrote here e to the 2 pi I times a bracket quadratic n root 2 times brackets n root 3. That's an approximate quadratic. It's a 1 over 100 approximate polynomial of degree 2, in fact. And in parallel to the theory of approximate groups, I've basically shown you all of the approximate polynomials. So it turns out that every approximate polynomial is at least related, correlates with one of those bracket quadratic polynomials. And this is a deep theorem. In something like the form I just stated it, it's due to Tau and Ziegler and myself. But it relies on intuitions that originally came from ergodic theory, and in particular the work of Furstenberg and Weiss and Host and Kra and also Ziegler. Now, there turns out to be a link with approximate groups. Unfortunately, I don't have time to tell you exactly how that works. But this was really discovered by Gowers. The deep direction of this was discovered by Gowers. So it turns out that classifying approximate quadratic polynomials is quantitatively equivalent to classifying approximate abelian groups, approximate subgroups of Z. And in fact, in both subjects, there are unsolved quantitative problems. In fact, the bounds that we have are out by an exponential. So to solve that problem, you could look either at approximate groups or at approximate quadratic polynomials. The other thing I should at least pay lip service to, these bracket polynomials that I showed you, the fractional part operation is very unnatural in many ways. It's a real pain to think about it. And there's a different way of understanding these approximate polynomials in terms of what's called nil sequences. So nil sequences are something that, well, they are constructed using certain automorphic functions on nilpotent Lie groups, and I'm not going to go into that today. But that's somehow the right way to understand these approximate polynomials. So there's a deeper theory there. Let me go back to doubly prime progressions. So remember, I asked this silly question, are there 100-term progressions of primes whose common difference d is almost a prime? And the best I can hope for is 100 factorial times a prime. And the answer is yes. And there's even an asymptotic. So what are the ingredients of the proof of that? Well, the theory of approximate polynomials is the main ingredient, the classification of approximate polynomials. And as I've just said, that intimately relies on the theory of approximate groups, at least over the integers. There's actually a lot more involved in there as well. So you need sieve theory to construct some majorants for the primes. And then once you've done all that, you need to show that some number theoretic functions, like the Möbius function, are actually not approximate polynomials. And for that, you really need to do some actual number theory. Okay, so now I'm going to turn to the final part of my talk, where I'd like to talk about something new. So we've heard a lot recently about gaps between primes. I think everybody in this room would know that Zhang recently proved that gaps between primes are infinitely often very small. At most 70 million and now reduced to 246. And in all the fuss about that, people have overlooked large gaps between primes. So how big can the gap between consecutive primes be? So what is the largest gap, g of x, between primes less than or equal to x? Now, there's an obvious result here. It's at least log x, or asymptotically log x. And this follows from the prime number theorem. Just the average gap between primes less than x is at least log x. The conjectured truth is the square of log x. But we can't prove that. The best result that's known on this is the kind of thing that gives analytic number theorists a bad name, because of the number of logs involved. But Rankine proved in 1938 this bound. And, okay, so it looks a bit ugly, but there's actually a very natural argument, which when you optimize the argument gives you this. So since 1938, Rankine proved that with a constant 1/3, and it's been improved several times, and the best now is 2 times e to the gamma. I have to admit, I don't know what that is. It's going to be about 4 or something. Now, Paul Erdős was interested in large gaps between primes, and here there's a picture of him discussing this problem, actually. And Paul Erdős used to offer money for problems in the days when there wasn't big money involved in mathematics. So actually, this was the problem for which he offered the most money, $10,000. It's just to improve Rankin's bound. That's this bound of log x times log x times log x over log x cubed, just to improve it by some function that tends to infinity. And it's that I'd like to announce a proof of. The answer to that question of Paul Erdős is yes. And this is a theorem of Kevin Ford, Sergei Konyagin, Terence Tao, and myself, which should appear on the archive later this week. And the proof of that theorem uses these doubly prime progressions that I talked about earlier in the talk. So in the remaining 10 minutes, I want to just say a few words. This will be not too technical, but probably the most technical part of my talk about what have doubly prime progressions got to do with finding large gaps between primes. So the basic strategy here, as in all previous works on the problem, is to study a different problem called the Jacobs-Tau problem. And the Jacobs-Tau problem is the following. You take an interval 1 up to y, and you want to sieve it by primes less than x. And what that means is that for every prime less than x, you get to remove one residue class modulo that prime. But you can choose which one. And you want to make y as big as you can, such that this sieving removes all of the elements of 1 up to y. So obviously this becomes harder as y increases. But how hard does it become? Now, if you can do that for a large value of y, then there's a variant of the very well-known construction of large strings of composite numbers. So you choose by the Chinese remainder theorem a number m that's congruent to minus ap modulo p for all of the primes less than x. And then m plus 1, m plus 2, up to m plus y, they're all composite. So there's always a prime that you can use, prime less than x, that divides one of them. And actually, the well-known construction involves taking all of the APs equal to 0. But you can actually do better than that. So I want to look at the Jacobs-Tau problem. And let me remind you that you start with the interval 1 up to y, and you want to remove it with congruences modulo primes less than x, at most 1 for each prime. And you do it in 4 separate steps. So first of all, you use some of the primes, the ones that are less than log x, and in another range between z and x over 4. So this already removes from the interval 1 up to y everything except the primes between primes up to y, and a set of elements called the smooth numbers, which means that all of the prime factors are less than z. And you choose z so that there aren't many of those smooth numbers left. So you basically got primes between 1 and y. So now we have just the primes between 1 and y. Now use some more of your primes, the ones less than z and bigger than log x, and use a random sieve. So just choose the APs independently at random. So that removes some more elements. And again, if you choose parameters correctly, you're left with a set of size, let's say 10x over log x. Now, which primes p have you got left? Well, we didn't use any prime bigger than x over 4. So we've still got all of the primes between x over 4 and x. So let's use now the ones between x over 4 and x over 2. And here's where we use the doubly prime progressions. The set R of things that I'm left with will have many of those doubly prime progressions. So that's progressions of length 100 with prime common difference. Or not prime common difference, but 100 factorial times a prime. You need much more than that. You need to know that it's well covered by those. But the point is that an arithmetic progression of primes of length 100 allows you to use these congruences mod p very efficiently. You can remove 100 elements at a time. So every time you see a progression of length 100, whose common difference is 100 factorial times a prime, you just throw out all 100 of the terms of that progression. So it's much more efficient than just removing them one at a time. And then at the end, you have to do some cleaning up. So you still have half of the primes left, and you have to just use those one at a time to clean up the mess that you're left over with. And that's the end of my talk, so thank you very much for listening.
Thank you very much for this very exciting talk. Are there questions?
I think I have two questions. The first one is you talked about approximate groups, but what you really described is approximate subgroups. Is there sort of a useful concept without fixing the ambient group? And the second question is...
Can I answer the first one? So that's a good question. And there are I can actually answer it in two different ways. So there's a sort of less extreme answer and a more extreme answer. So you could start not inside a group, but with an operation that's already known to be a sort of locally associative. And for that problem, the theory that we developed applies. And moreover, we actually need to work in that setting. The more extreme setting, in which you have an operation that's only somewhat associate, things seem to break down horribly. You can't say anything useful as far as I know.
And this Erdős question was to improve this previous estimate, and you announced that you can approve it, but I didn't see how good the improvement was.
Well, so the question is, what is this function f of x by which we improved Erdős's bound? And the answer is it's probably the worst function that's ever appeared in number theory, because it's ineffective in two different ways. So it's just a function that tends to infinity. We use estimates on Siegel zeros, which are ineffective, and we use an ultra-product construction ultimately inside the proof of the inverse conjectures for the Gauss norms, which is also ineffective.
Great.
Thank you very much.
Yeah, here.
Yes?
Here.
Yeah.
Yeah, here. You are there? Here. Yeah, here. Here.
Oh, sorry. Hello.
Yeah. In your simulation, is from the root to the boundary and stuck there in the M16. Looks like this. And then actually, this one is from the root to the boundary. The probability is very small. And then in the computer simulation, and then the computer identifies the small number as 0. And then this can be stopped there. If the computer accuracy is improved, and then your graph, your tree maybe go further. Maybe M632.
I have to say, I can't really hear the question. I'm sorry. Maybe we could talk about it afterwards.
Sure. Yeah. This is maybe it's the computer error caused the stop. Yeah. Thank you.
Well, let's thank the speaker again.